now. So I'm going to bring this up and share my screen. We're looking at 12.16. Whoops, not that. We want this. Whoa, too big. And we probably are a page up here. And I'm going to stop my video just to cut the lag. Sorry about that. All right. Look at this problem. I love it. So consider a car rounding a curve on a flat track. So they're basically driving in a circle. And to make that clear, I'm going to show the video. You got this car going around the track like this. So it's a flat track. And so here's the center of the circle. The car's driving this way. There's towards the center of the circle. We don't have any of this banked curve crap. So we don't have any of this. All right. Flat curve. And let me go back to the problem and stop my video. Okay. And so in this case, you could imagine it's accelerating this way. There's AC. Now, if you recall, we can get rid of acceleration and replace it with a fictitious force pointing the other way with magnitude MAC. So the fictitious force is not AC, it's MAC. But now if you look at this, this thing is viewed as a statics problem. So what we do is we take a problem where the car is moving, the acceleration with a fictitious force, then treat it as a statics problem. That's the cool way to use these fictitious forces, all right? So I'm going to go to the solution now and talk about this one. Right here, maybe? And so this is what the normal FBD looks like on this side. This is the normal FBD. And then what I did is I said, set A equal to 0 and put in this fictitious force. Notice the fictitious force acts at the center of mass. All right. And there's a lot in this problem to digest. I want to slide up here. That is what I tried to emphasize. And now, one of the things that's tricky here, and I think this is, that one's just standard chapter 6. So that's a good review. Part A is just standard chapter 6 methods. So if you don't get part A, go revisit that problem in chapter 6, right before the banked curve problems. So now you might be wondering here about the frictional force and why it's all on one tire. Okay, so if you might be wondering, why is this frictional force being applied here? Why isn't it on both tires? Well, in part B, the car is about to tip over. And if the car is about to tip over, you got to think, which way is it going to tip? That's what this fictitious force helps us understand, right? The red force, even though it's fictitious, is tending to tip this thing that way. The green force is tending to torque it this way. And so we see that if you go too fast, it's going to twist this way. And that makes this the logical pivot point, which means this tire is coming off the ground, which means this is the only tire in contact, blah, blah, blah. All right. So the logic there is it's going to twist this is good. If you go too fast, it's going to twist this way, which means this wheel is going to lose contact, which means this is the pivot point. And this doesn't make any sense. Is that so far so good? Hopefully that's good. And so once you get there, if I choose this point as the pivot, these two forces don't contribute torques. I've got a lever arm here. And then I've got a lever arm right here. And there we go. I'm off to the races. This is going to be something, I forget what I called it, X over 2, and this would be something like Y over 2. And maybe I called them X and W in this problem, I think. So let me look in the problem there. Oh, so I'm sorry. I called it W and Y or something. Oh, I see. So it's not Y over 2. It's just Y, and this X down here is a W. Sorry about that. So this part down here would be that would be W over 2. And this whole thing is why it says. And so if you've ever seen the specs on a car, you've probably seen them talk something about the wheelbase or the width of the wheels, and you might also see the center of mass in there. So if you're trying to do a performance vehicle, we see that the location of the center of mass matters, and the wheelbase. So obviously the wider your wheelbase, if I scroll down here, if you're into this stuff, this is where this stuff comes from. If you're wondering, you get these results. And so the largest speed that you can get depends on the width of the wheels and also the height of the center of mass. So the lower your center of mass, the faster you can go. The wider your wheels are, the faster you can go. And obviously, the bigger radius of turn, the faster you can go. So if you've ever done anything with cars, this probably makes sense to you, but this shows you how the physics matches up to your intuition. All right, that's probably enough on this problem. I'm going to stop for a second. Any interesting questions about that one? Oh, so let me catch up. Yep. Okay, so Jay got her question, and then let me read Dane's question here. Not related. Is the final exam graded the same as the last one? Meaning, Dane, it's probably going to be something like something like that. But what I did is I just took I took 86 and so I'm going to ask you 4. That way it's not so rushed. So each oral exam question would be worth about 25 points. All right. Dane, does that address your question? Wherever you are there. Yep. Okay. So yeah, so if you get an 85, that would be very close to 100 points. That'd probably be like a 98, and then or 98.5 maybe or something, or 98.7. Yeah. Okay, cool. All right. Let's take a look at 12.19, I think was the next one I said I would do. So now 12.19. And hey, you guys are all troopers. Hey, I appreciate all the hard work you're doing on your own. Sorry this class sucks now. Let's keep going. All right. All right. This is something I want you to know just for your own knowledge, okay? We've been talking about what causes a block to slip versus tip. Okay, and so notice here we go. We've got the center mass, so we've got a high centered object. The center mass is high up. So if I could, I'm going to zoom in here really big and get over there. All right, so we've got the center mass here. So this is mg, right? Now, if this thing's going to tip over, you've probably noticed this over and over again. If it's tipping over, I'm going to start to draw the pivot point right there. So if it tips over, the line of action for mg is actually beyond the tipping point. So at that moment, there would be a frictional force. Whoa, not what I wanted. There's going to be a normal force. Oh my gosh, where's my arrow? There it is. I've got a normal force this way and a frictional force this way at that pivot point. And so we could get this thing tipping over here. And let's see if let's go look at the solution for this one and see what else I wanted to say about that one. I just don't remember right off the top of my head, so I got to look it up. And so this is yeah. So what was part A? Oh, and so I just addressed that one. The normal force is at the corner, and is so yeah. That's what I was trying to give you a clue there with the picture. anytime the line of action for MG goes beyond the pivot point, that's when it would tip over. So we see that it's just slightly larger than that pivot point, right? So that line of action is beyond the tip. That's when things tip over. So if you remember one thing from this problem, that's it. Anytime you have the line of action for MG going beyond the pivot point, it tips instead of slips. It tips instead of slips. Okay. And that really is all I want you to learn from this problem. But let's see if there's something else worth noting in the solution. Oh, I found some boring crap. Okay, cool. Okay, there's a typo there. But for a uniform cube, the line of action runs through the pivot there. So, okay, cool. So you could basically, this is why tall objects tend to tip and short objects slide. So you probably noticed this if you put a, oops. And let me show my video here. So if you have an object like this and you start rotating it, this one tends to have a low center of mass because there's a lot of weight down here at the bottom from these paper clips and stuff. So that's why it's going to, oh, and there's also a small coefficient of friction. But if I put this here, the taller it is, the more likely it is to tip over. So you can see it starts to tip at some point, and that's I'm forcing the pivot here. The taller the object is, the smaller the angle needs to be. So if I tried to use an object like this, okay, so in this case, it should probably, you can see it's not going to slip. And that's because you have a high center of mass and a low aspect ratio. So it's really easy to get, in this case, right as it starts to tip, the center of mass is right there. The line of action runs from the center of mass through the pivot and it tips instead of slips. So yeah, if you care why tall objects tend to tip over instead of slip, that's it. If you don't want to do the rest of the problem, cool with me. All right. Any questions about that? Yeah, man. Yeah. Or Jay. Sorry. I just called you man, Jay. Sorry about that. All right. Yeah, cool. All right. Let's go. Let me do that last problem here. And then if we have time, I'll keep going if you want. And if you don't want to, just leave whenever you want. Let me scale this back a little. And go up to 12. I think it's 15, right? Ooh, this is a good one. This is a good one to remind ourselves. So maybe you could try and, I'm going to give you a second to set this problem up. Try not to look at the solution. Give yourself 3 minutes. All right. See, or 5 or whatever. Okay. See what you can do. And I'm going to stop my video. Sorry about that. Again, we're looking at 12:15. I'm not going to say anything for a couple of minutes. I'll set my timer here and I'll watch it. Okay. I'll give you 3 minutes and then I'm going to start going over the solution. How are you doing, Trey?
Doing pretty well. Things have been going good.
That's cool. How'd you end up doing on that physics test?
You know, oddly better than I thought, which has been the tradition, but I don't know. This time I thought it was much, much worse than normal. Like normally I always feel, oh, I did terrible and I got, like 95 or something like that. This time I felt, okay, I truly genuinely did terrible. There's no way I did well. And I got like a solid like B plus and like, okay.
That's sweet.
Good enough.
I see there's a question here I should be answering. Sorry about my chit chat there, Phil. Phil, what's your question? Were you talking about the tipping there? Yeah, so I'm going to try and show you in a whiteboard. Okay. So imagine you have a block right here, and let's say its center mass is right about there, okay? Let's say that's the center of mass position. Right about there is the arrow. And then if I could, just drawing the line of action here. Now, at this moment, the block is on the verge of tipping. I'm going to say that again because all the lag. This picture is on the verge of tipping. In that case, if it's on the verge of tipping, right, you think about this thing, it's about to start going this way. When it's about to lift off, this is the only point in contact. Now, Phil, if you really want to learn more about where is the average normal force, I wrote up problem 12.22, if you care, on page 109. So if you're interested in learning about the location where a normal force is applied and how to figure that out in general, that's described in 12.22. But if you're on the verge of tipping, it's always about to go. So that's why this red dot here is the only point in contact, and that's why the normal force is there, and why friction. Oh, whoops, that's not the direction of normal force. Sorry about that. Because this is on an incline, right? So there we go. This would be the direction of the normal force, and this would be the direction of friction there. Phil, does that address your question? Yeah. Okay, cool. And so hopefully everybody now has had a chance to look at 12.15. I'll give you 30 more seconds. So 12.15, and obviously you don't have to wait for me if you've already written down your equations and stuff. Looking at 12.15. And go ahead and do it. Is it this one? So this is very similar to the old ladder problem, but I do want to alert you to something up here. This is a force that we didn't have before, this friction 2. So hopefully you can see that on my screen now. So the wall has friction. And notice we're going to have to label everything carefully now. So I've got normal force 2, which is coupled to friction 2, normal force 1, and friction 1. I've got my lever arms here. And so let's see what I did here. Vertical forces, horizontal forces, and let me see. Ooh, let's just go through this one and make sure I didn't screw up. I don't think I did, but let's look at it. So the vertical forces, I'll circle in red. Whoops, oh my gosh. All right, so now let me get back. So here's a vertical force, here's a vertical force, and here's a vertical force. So that's why there's 3. Now I'll do these other ones in this kind of light blue color. So there's a horizontal, and there's a horizontal. So that's why there's these 2, left equal rights. And now I'll clear all those drawings. Now the torque's about bottom left. Let's do that in purple. So this is my pivot that drops out this one and this one. So L, I did a lever arm, it looks like, or you could say this is L over 2, and then sine of 90 minus theta. Hopefully you remember that sine of 90 minus theta is cosine of theta. So you could use that either way. So this is R, F, sine theta is actually cosine theta in this one, because theta is actually 90 minus theta. And we got that, we're good to go. Notice you get the same result with the lever arm. So that was this, and that's a torque that's positive. Now the other ones, I chose to call those negatives. It doesn't matter because the sum of torques equals 0, but I'm getting really messy here. So I'm going to clear this out. Here's my pivot point. So now you could say this is the lever arm for that one. And notice that is, let's see, if this is theta, this side is L sine. So notice the lever arm for this one is L sine. Now let's do the other one and say, how about orange? I haven't used orange. This one is this line of action. And this distance right here is going to be L cosine. Are there other ways to do this? You bet. And somebody probably just brought that up in the chat, so I should take a look. Jay, you can choose any point you want as the pivot. So remember, this is not rotating. And so you could choose the center mass if you want. Now, Jay, why do you think I chose this point? What is the advantage of choosing bottom left versus the center? Correct. Now, do you agree I could have also done the top right? What about doing the sum of torques about this green point over here? Could I have done that? You could, but it would suck. And that's why we didn't choose it. So the three logical points are this one, and they all have pros and cons. All right. They all have pros and cons. But hopefully this equation here, whoops, this part here, I just want to clarify, this was force 2. And this was the lever arm for that. So it looks like I did all lever arms here. If you get used to it, it's kind of cool to do lever arms. All right. It doesn't work in 3D though. But for this class, we're doing mainly 2D here. So I can't see putting a 3D. I'm not putting a 3D statics question on. All right. I'm not doing it. But those of you that have to take statics, you'll do it there. So there's 3 equations, 1, 2, 3. Let's check how many unknowns we have. All right, N1 unknown. Friction 2 unknown. Mass given. G given. Need another equation. Friction 1, that's a new unknown. Normal force 2. Uh-oh. We're up to 4 unknowns, right? This is not good. We're up to 4 unknowns. And we only have 2 equations. Let's see. Here we get a this. Do we know what L is? Oh, it drops out at least. So we got mg2, I know. Unknown. Is theta given? I'm going to assume theta is given. My apologies. I should have said that. I'm going to write that on my note. Assume theta is given. Oh, that's right. Because in ladder parts 1 and 2, theta was, I think, I don't know. I'll have to read that. So 12.15, assume theta given. All right. All right. So in this case, let's assume this is given, but we still have unknowns. So I'm going to need more equations, and here they are. It's this on the verge of slipping. And then we're going to assume this is true. So now we've got some equations we can work. And the rest of this is kind of boring, just kind of cruise through the math. I think there's one interesting thing in here, so maybe it's worth looking. So notice I just put in the mu n2 and mu n1. Aha, this allows us to get rid of this. So notice you're going to get a mu squared there, right? You get a mu squared somewhere. Oh, I see. I went the other way with it. But yeah, so one of them is going to be, you get a squared somewhere. And notice you get this weird result that's got a 1 plus mu squared somewhere in the equation, depending how you want to do it. There's mu. Woo! Whoa, yeah. Okay, that one's tricky. So all this stuff up here is probably good practice for your final. To be honest, I probably wouldn't do this last part to you, this quadratic formula on a tangent theta. At least not on your final. I just tend not to do those nastier versions on the problems for the final. So yeah, it's great practice up to there. Is that good for that one? I'm just putting some in the chat for you. So it's similar length. Similar length to last time. Expect about 12 to 15 problems. And there's going to be at least one that's super nasty. So if you could do nothing else but identify that one and skip it and save it for last, you usually have a good, there's going to be a lot of conceptual stuff and things like that. Yeah. We still have a couple more minutes. I just want to show you one more here. And you guys are all troopers, and I know I'm getting worse and worse as the semester goes on, as my energy level drops. But I do want to show you something else that's kind of cool. This problem, 12.17, if you want to look at it, this foreshadows how you build a bridge. Think about it. There's a truss sitting there. And so there's a cool trick. And I'll be honest with you, problems like this one, not on the final. So if you're still here and listening, just know that if I asked you to do this problem, you should still do it, but don't stress out about it. So follow along with the solution and just learn this new technique, which I want to show you right here. Where was that? I think this is the trick that you do for that. You cut the thing in half and you just do a free body diagram for the left half and the right half. And notice this is the weird thing that happens here. And I'm not going to say too much more about this, but we say there's going to be forces from the pin on this thing. And so there's going to be an AX and AY. And there's going to be, by Newton's third law, they point the opposite way on the other one. And so this is a force from the tie rod. It's in tension, right? The ladder's trying to the ladder is trying to fall apart like this. So that's why you put a tie rod in there. It's got tension. So as these try to slide out, that tie rod in between, the tie rod in between is going to be pulling on it and exerting a tension on it to keep it from sliding outwards. So this red thing here is trying to pull on it to keep it from sliding out. And so if you're interested in where civil engineering might take you, that's a little foreshadowing there. So that's probably good enough. Let's call that good and end the live stream at least.